All right, open up your book to section 6-2. We're on page 284 in your book, and the title of this section is General Sinusoidal Graphs. Our objective is to, given any one of these sets of information about a sinusoid, we want to be able to find the other two. So whether you're given the equation, the graph, or the amplitude, period of frequency, phase displacement, and sinusoidal axis, given any one of those, be able to find the other two. And we saw in the first half of this section how we were able to do that. So let's continue with a couple of examples. Take a look at example number 3. This is on page 289 in your book. Example 3 there says, the figure there shows the graph of a quarter cycle. So they've only got 1/4 or 1/4 of a cycle of a sinusoid. And they want you to write a particular equation of, and check it by plotting it on your graph. And sometimes they'll give you a quarter cycle, sometimes they might give you just a half cycle, or they might give you the whole full cycle like we started with. But the key here is if they only give you a quarter or a half, just realize they have to give you a very careful quarter or half that they've picked here. All right? Based on the sketch that I see here with this one, they've actually given us the half that goes from the sinusoidal axis right here down to your lower bound right here. Right? It looks like at 24 degrees we're hitting our low point and starting to turn around and head back up is what it looks like. So they have to give you something that goes between these upper bounds or lower bounds or the sinusoidal axis. It can't be somewhere in the middle of those. All right, so they have to carefully pick that for us. All right, so we want to find the equation of this. So we need to find out our A, B, C, and D. So let's start out with our amplitude. The amplitude is this distance right here, or the absolute value of that is our amplitude. So 8 minus 3 sounds like 5. It's going to be our amplitude. The sinusoidal axis is the line that goes right down the middle of this thing, so that's our value of 8. For our phase displacement and our period, well, they actually only gave us a quarter cycle here, but I can use that to help us figure out what the period is going to be. From here to here, that's 1/4. I'll write it that way. 1/4 of the period, which is equal to, what's 24 minus 17? That looks like 7 degrees, right? 24 degrees minus 17 is 7 degrees. You want to know what the period is equal to, so if you just take this and multiply that by 4, right? If I multiply everything here by 4, that should tell me what the period is equal to. So what do we end up with then? The period would be 4 times 7. Period is equal to 28 degrees then. So even though they only gave me a quarter of the cycle there, I can still figure out what the period is going to be. And then the last thing I need is I need the phase displacement, our D value, and that's not really in the sketch here. I do have the location of the lower bound, but I want to find the upper bound here for us. So if I go 5 units above our sinusoidal axis, that would be, I'm going to try to measure this about accurately. That would be somewhere about right here. In fact, let's sketch the rest of this curve here, or try to sketch the rest of this curve in here. So it would do something like this and then start coming back down, right? That would be a half of the cycle if they'd given us that. So we want to know the location of this high point is what we're looking for. Well, it turns out that if you take your period and you break it up into 4 equal parts, it crosses or it hits the upper bound and lower bound and the sinusoidal axis at nice values there. In fact, let me sketch the rest of this sinusoid and we'll mark those key values that we're talking about. So if I look at where I hit the upper bound to start with, and then where I hit the sinusoidal axis that first time, and then where I hit the lower bound, and then I'm back to the sinusoidal axis, and then at the upper bound again, those are all 1/4 of the period apart. So in other words, this we figured out was 7 degrees here. This here is going to be 7 degrees. This is 7 degrees, and this is 7 degrees, that interval. So with that, I can then figure out where my high point is at. If I just subtract 7 degrees from 17, that leaves me with 10 degrees there is where I'll hit that first upper bound, which is my phase displacement I'm looking for. All right, so we should be able to write our equation then. We're going to write this in terms of cosine. I like using cosine, and the book does as well, just because of the fact that you're finding the upper bound for that phase displacement, which is usually easier to deal with. So it's c plus a. C is your sinusoidal axis, that's 8, plus a is our amplitude, that's the 5, times the cosine of, remember it's 360 divided by your period, which we found was 28 degrees, times theta minus, and then d, our phase displacement we found was 10 degrees. Okay, so there's our equation of this. They said write the equation, then plot it on your grapher. So let's grab our calculator and try sketching that. Okay, so with your calculator, again, make sure you are in degree mode. If you're not, then get switched over to degree mode. But go to your y equals menu, and we'll put in our equation. We have 8 plus 5 times the cosine of 360 divided by 28. Again, you can simplify that, but I like leaving it in that form because that means that when I look at that quantity b, the denominator is the period of this. When it's in the form of 360 divided by some number, that number is the period. And then x minus 10 degrees is what we found for our phase displacement. All right, and then again, I'm just going to put this in the window that we came up with for our kind of general sketch or a rough sketch that we came up with. So we went from 10 to, I guess we didn't mark the last value here, but 10 plus 28 would give us 38 would be the full period. And maybe we'll put this at 7 here, since that's what, actually it's not going to work out very nicely. I'll just leave that at 1. And then for our y values, it was the lower bound was 3, our upper bound was 5 and 5. That was 13. Yeah, scale of 1, that'll be fine. And again, we should see this thing sketch and get one period, and it should fill the screen from top to bottom. That's what we're looking for. I wouldn't say that this is necessarily the best sketch of it, but I at least know that this equation is in fact fitting the description they've given me. In fact, if you wanted to narrow it down to just the quarter cycle that they gave you and only look in that window, that would even be more precise there, so you know you're getting exactly what they gave you in the problem. Let me grab a picture of that. So that looks pretty good there. All right, that's what they wanted us to do for problem number 3, or example number 3. Let's take a look at the next example. Example number 4, which is actually a continuation of that same problem there. It said for the sinusoid in figure 6.2k, which is actually the same one that we just were working with, write the particular equation. And they're going to ask you to write it a couple of different ways. And actually, we're going to add to this list here. But they say to write it as a cosine with a phase displacement other than 10. Well, we just wrote this equation with a phase displacement of 10. And they want us to pick something other than 10. So again, if we just look at our sketch here that they gave us, we use this value right here as our choice for our phase displacement. That was 10 degrees. But if I just add on or subtract off any multiple of the period there, that'll give me another choice here for D. In other words, my phase displacement could be 38 degrees. That's 28 degrees later. That will certainly work. So let's write it that way. So for part A, we would have y is equal to our sinusoidal axis is still 8. Our amplitude is still 5. We're using cosine, they said. Our period is still 28 degrees, so it's still 360 over 28 degrees times theta minus, and again, the only thing we're changing from the previous example is this value of D, so it's minus 38 degrees that we wanted. All right, that'll work. Again, you could add another 28 degrees of that and find another option, or subtract 28 from the 10 and get another option there. You can go either direction. They didn't specify whether you're adding or subtracting a period. All right, for part B now says to do this in terms of sine, and that's what we should recognize here is that when we're dealing with a sinusoid, you've got two options. Am I going to write this in terms of sine or cosine? I would strongly suggest that cosine is the option you get to pick, or if you get to pick, that you choose that one, because finding that upper bound is usually easier. But if we're going to do this in terms of sine, the good news for us is everything that I have written down here in terms of cosine is exactly the same. The only thing that changes is your phase displacement at the very end. With sine, the phase displacement that we're looking for is I have to be crossing the sinusoidal axis and increasing. So this place right here, I can see that I'm crossing the sinusoidal axis and increasing. That's at theta equals 3 degrees. So that's going to be my choice here for my phase displacement for this sine function. So let's write that. We have y is equal to 8 plus 5 times the sine of 360 over 28 degrees. I guess I don't need that parenthesis here. I'll get rid of it. You can add it in there if you want, but it's not necessary. Times theta minus, and then instead of the 38 degrees like we used for cosine, it's 3 degrees for sine. Very slight change there. In fact, only 2 things changed as I go from cosine to sine. I have to change the trig function, obviously, and I also have to change the phase displacement. All right, let's take a look at the next part of this. It says for part C, they want us to do this in terms of cosine with a negative vertical dilation factor. So that's the value of A that they're talking about. So they're talking about letting A be negative. All right, so for part C, in fact, let me mark that here. That we're talking about A is less than 0 now for these 2 examples that we're going to write down. So for part C. Again, the good news for us is that the A, the B, and the C are all going to be the same here. It's the D value that's going to change. I should say the A is going to be negative, but otherwise it's 5. So I've got to figure out what exactly is going to happen with that phase displacement. And to help you do that, I suggest you go back to your cosine function, the parent function, and think about what happens if you take the opposite of that. So in particular, we know that y equals cosine of theta. Has a sketch that looks something like this. It starts up here at its high point and then kind of oscillates back and forth like this, right? Question is, well, if I'm going to take and make A negative, that means I'm actually going to be looking at y equals the opposite of cosine of theta. And that's a topic that we talked about back in chapter 1. If you take the opposite of a function, you're just doing a vertical reflection of it. So a vertical reflection of cosine, that means instead of starting at its high point, we'd be starting at its low point and doing this. So when you make A negative, the leading coefficient there is negative, which means that I'm looking for, instead of a high point, I'm looking for a low point on my cosine function. All right, so let's take a look at our equation up here. And maybe I'll do this in a different color. So now, instead of looking at the 10 degrees or the 38 degrees, I need to find out where cosine hits the lower bound. And right here, it looks like it hits the lower bound. That looks like my choice I'm going to have to pick for D in order for this to work. So let's check that out. So we have y is equal to, again, your A, B, C all stay the same, except we're going to make the A value negative. So it's going to be 8 minus 5 times the cosine of 360 divided by our 28 degrees. Times theta minus, and we just figured out our phase displacement has to be 24 degrees. All right. Let's take a look at part D now. Part D says now we're going to do a sine with a negative vertical dilation factor. So we want to go through the same thing by using sine. So again, I would suggest to you that we go back to our parent function, y equals sine of theta. Think about what its sketch looks like. Remember that the sine function does something like this. It's crossing the sinusoidal axis and increasing as it goes through the origin. That's what our parent function looks like. So if I were to graph y equals the opposite of sine of theta, so that's what they're asking us to do, make A negative. What's that mean? Well, that's, again, a vertical reflection of this. So if I take this function and do a vertical reflection, that means now I'm going to be decreasing as I go through the origin. I'm decreasing as I cross the sinusoidal axis. So what I see there is that when I make that negative, that the point that I'm looking for is I'm crossing the sinusoidal axis and I'm headed down. I'm decreasing. as opposed to what the parent function does. So let's look at our graph here and find that point that we're going to use. And let me do this in a different color here. So I got to be crossing the sinusoidal axis and decreasing, which looks like this guy right here will work. That's at 17 degrees. Will be my choice that I'm going to make for this equation. So let's write out our equation then. This one's in terms of sine. Y is equal to 8 minus 5. Again, we're making a negative. And we're going to replace this with the sine of 360 degrees divided by our 28 degrees. And that's times theta minus. And again, the value that we came up with was 17 degrees, right? Is our value for our phase displacement. Let's just grab our calculator and verify that we are in fact getting the same results here. So go ahead and grab your calculator and let's sketch these along with the original function. All right, so let's go to your y equals menu again. I'm going to leave y1, that was from example 3, still in there. I want to sketch that along with these other two functions here that they've given, that we came up with. So we came up with y is equal to 8 minus the 5 times the cosine of 360 divided by 28 degrees. And that's times x minus, and we came up with 24 degrees was our phase displacement for that when we make a value negative. A was negative 5 there. In fact, to help me sketch that, let me just sketch that with this little tracer thing here. That's that little circle there that we'll sketch on top of it. Hopefully it comes in sketching right on top of the function I've already got there. Let's go ahead and graph the other one along with it, so we'll see all three of these graphed together. 8 minus the 5 times the sine of 360 divided by 28, and that's times x minus 17. 17 degrees was our phase displacement we came up with for our sine function when we do a vertical reflection to it. We're looking where we cross the sinusoidal axis and we're decreasing. And let's do the same thing there. Let's mark this with, mark this with this little tracer. There we go. All right, so let's sketch all three of those. Hey, check that out. So our cosine function looks correct there. It's tracing right on top of our original equation we had. And check that out. So is our sine function, tracing right on top of that. Good way to double check to make sure that in fact you're doing it right. Sketch the original and then sketch these other equations in there. Just make sure that they all match up. But again, you should be coming up with the equation first and then going to your calculator to see if in fact these are the right equations. It should not be a case of you're using your calculator to kind of guess and check to see what numbers you need. That's not what we want to be doing. All right, let's. That's the end of their question, but let's modify this question or add to this question a little bit more, because we could have other values that are negative as well. They had us make the value of a negative. We could have b being negative as well. So let's do that. In fact, we'll start out by saying we're going to make b less than 0. We'll go back and make a positive again, but we'll look at what happens when we make b less than 0. So that was d. Let's call this e then. All right, so let's think about what happens there on our cosine function for e here if we make the b value negative. Well, go back to your parent function again. I'll go ahead and sketch that, but hopefully that's a sketch we're getting more and more familiar with. Cosine does something like this. So then if I take and make b negative, so I'm talking about a horizontal dilation factor that's negative. So you got the cosine of a negative theta here. And hopefully we recognize that from chapter 1 that, oh, that's just a horizontal reflection of this function. So if you take this function and you do a horizontal reflection of it, take this graph and reflect it horizontally, you end up with the exact same graph that we started with, right? This thing would still do something like this. That turns out to be what it means to be an even function, by the way. If you recall, our definition of being even means you have symmetry across the y-axis. Cosine turns out to be an even function. And it turns out then with cosine, if I make b negative, it's the same as if I had left it positive. So actually, we've already done that work. Let's go refresh our memory, I guess, as to what our phase displacement was for that. That was the 10 degrees then. That's this guy right here. If I do a horizontal reflection of this function, it's the same as the original, which means that I can use the same phase displacement of 10 degrees. So I still will have a slight variation in the equation because I'm making b negative. But it's going to be y is equal to, oops, 8 plus 5 times the cosine of 360 degrees over 28 degrees. Oops, we're making that negative, right? Maybe I better make that a little bit clearer here. It's the cosine. I'll put that in parentheses so you can see that that's negative. Cosine of a negative quantity there. And theta minus, and we just said that we can use the exact same value for our phase displacement as our original equation was. So 10 degrees will work. All right. Let's see what happens when we do the same thing with sine. We're going to make b equal, b is going to be a negative number, so it's going to be a negative 360 over 28 degrees. But again, the question is, well, what does that do to our sine function? So again, go back to your sketch of your sine function. Sine is a function that does this, right, as it goes through the y-axis. It goes right through the origin. So what does y equals sine of a negative theta look like? Again, that's a horizontal reflection of that function. So a horizontal reflection of that function would end up looking like this. So it would turn out in doing this. I'm decreasing now as I go through the origin. Well, that's kind of interesting because that was the graph we just looked at. That was the same as the opposite of sine of theta. And oh, that's another property we learned back in chapter 1. The functions that are odd have this property. They have symmetry about the origin. If you rotate 180 degrees around the origin and you end up with the same thing you started with, or another way of saying that, you reflect across the x-axis, reflect across the y-axis, and you end up with what you started with. That's what it means to be an odd function. So turns out that the same value of theta that we came up with for a negative sine of theta can be used here. That was this guy right here. That was the 17 degrees. We'll go back up here and mark that. But I'm looking now for where I cross the sinusoidal axis and I'm decreasing, which is what I'm seeing happening right here. So the 17 degrees will work for that. All right, so our equation then is y is equal to 8 plus 5 times the sine of a negative 360 degrees over 28 degrees times theta minus the 17 degrees. I suppose we could stop there, but we're this close, we might as well just finish this up. The other possibility that we have here for A and B, we looked at what happens if just A is negative, and we looked at what happens if just B is negative. I guess the next scenario here to consider is what happens if they're both negative. So let's do that. If A is less than 0 and B is less than 0. So let's call this G. All right, so think about what that means here. We're doing both a horizontal reflection and a vertical reflection. So let's do it in that order for cosine. If you do a horizontal reflection of cosine, think about what that looks like graphically. That's the exact same thing we started with. And then if you follow that up with a vertical reflection, that means that cosine at the y-axis is at its low point. So our phase displacement that we're going to use, I'll mark that on our sketch up here. The phase displacement is where the cosine function is at its low point. That's going to be right here. So the 24 degrees will work for this guy here. So our equation then is y is equal to, it's 8, and then it's minus 5, we're making a negative, times the cosine of a negative 360 over 28 degrees. Again, we're making b negative as well. And then it's theta minus, and again we said that we're looking for where cosine hits its lower bound. That was the 24 degrees is what we just marked on our sketch up above. And then finally for H, we'll do the same thing, but with it in terms of sine. So in terms of sine, again, thinking about what exactly does this do to the graph, think about what happens if I take that graph and reflect it across the y-axis, the parent function for sine, and then follow that up with it reflecting across the x-axis. And that should convince you that the graph is the same as what you started with, because it's an odd function. Think about that again. If you reflect across the y-axis first, that means your sine function's crossing through the origin but decreasing. It's on its way down. If you reflect that again now across the x-axis, now it's going to be increasing through the origin. So we're back to the same sine function that we already know. So if we mark that on our sketch here, mark that one last point, I just need to find out where the sine function is increasing and crossing the sinusoidal axis, which right here at 3 degrees will work. So we've got y is equal to 8 minus 5 times the sine of negative 360 divided by 28 degrees times theta minus 3 degrees. There we go. That is a very good little activity there. That's something that you should feel comfortable doing or get more and more comfortable doing. If you need to practice that a few times, then do so, but you should be able to take a sinusoid and write it an infinite number of ways. Okay, notice that you can change the value of maybe we'll write the general equation here. For all of these, you can change the values of 3 of these numbers, but you can't change the value of the 4th one. If I write this out, c plus a times I'll write in terms of cosine of b times theta minus d. Realize that you can change the value of d. All you got to do is keep adding on multiples of the period, going forward or backward. You can do that. You can change the value of b from being positive to negative. I'll put a plus or minus above that, indicating it can be positive or negative. And you can change the value of a. We just played around with that as well. We made that positive or negative. We'll put a plus or minus in front of that. But the c is set. C is your sinusoidal axis. You can't change that. All right? And I guess the other thing that you can change here, obviously you can change cosine, and you can switch that over to sine is the switch that we can make there. So there are plenty of things you can play around with in this equation here, and you should get more and more comfortable with changing those and see how that affects the equation and what the equation is of the exact same sinusoid using slightly different values. All right, that is the end of the second part here of section 6-2.